Okay, so, and they typically are taught in this order. Linear functions look like this. So make a tiny little picture underneath the word linear, just real small, folks. You're going to need to write more, so leave space on your page. Linear functions look like this when they're graphed. In other words, straight lines. Quadratic functions look like this when they're graphed. This would be the hoop, like that. Okay. Exponential functions look like this. They don't always have to start at the y-axis. Sometimes they can go past the y-axis. Just they kind of look like that, where we might say they only have one tail. Yeah, I'm thinking of the little arrow like a tail. It's just kind of like one tail. So if you look here, you get an idea. Just scroll. That's exponential. That's exponential. You understand? That's kind of what they look like. Now, there are two forms of exponential behavior. So let's write down exponential behavior. Two forms of exponential behavior. The first form is called exponential growth. And the picture of exponential growth looks like this. It's really better to see it every time. Exponential growth starts out small, maybe even at 0, and then you see it shoot up. And right next to this, I want you to write coronavirus. Do you remember back in March, in late February of last year, in Texas, there were only 3 cases of coronavirus.
Thank you.
I can show you the Google history of coronavirus cases in Texas. There was a time when New York had thousands, 20,000. We had 3 cases here. And we only, I believe, had something like 500 cases when we shut the whole country down in Texas.
Texas.
Now, what happened after that? Texas became the #1 state for new cases of coronavirus, over 20,000 per day. So what happened here is the number of cases started off small, and then it shot up like a rocket. So it starts off flat, and then it does real slow, and then it just goes boom. Kind of like a roller coaster, okay? Right? Like a roller coaster, just, or a rocket. Rocket's even a better
Power band on
thing about a rocket, okay? So that's the first form. And the flip side to exponential growth is called exponential decay. And decay doesn't have anything to do with like decay in the sense of like an animal. I'll show you what it looks like. Exponential growth, exponential decay. Actually, it might be easier to stick this thing on the same picture. I'll use a different color. Exponential decay starts off high, and then it gets real low, like this. An example would be hot water, okay? If you have a thing of boiling water, the temperature is very high. What is the temperature of boiling water? In Fahrenheit. Better be higher than that because your blood is 98.6. It's over 200 degrees. Okay, 212, is that right? 212 degrees? Yeah. Anyway, water boiling, it's very hot. And then it cools down rapidly down to whatever the room temperature is. Okay. If you put the boiling water into the fridge and the fridge at 30, if the fridge is at 35 degrees, then eventually it will reach this status of being like almost flat. But you see, that's what happens. So there's an exponential decay. So instead of rocketing up, it kind of rockets down. Okay. So there's a formula for exponential functions. This is going to lead us into an example. So this is a formula for exponential growth. Well, we'll just say exponentials. This is kind of the big formula here. And that formula is f of x equals a, open parentheses, b, close parentheses, raised to the power of x. The x is the exponent. And the x usually refers to time. Now, the b is 1 plus or minus the rate of growth or decay. In decimal form. A lot of this will become very clear when we start doing examples. It says 1 plus or minus the rate of growth or decay, and then I have decimal in parentheses. This a right here is the starting value. This f of x right here is the ending value. We'll call it ending or future value. So I want to jump right into an example with you so that this doesn't just all, this is the notes, okay? We got the notes. We have the meats. We have the notes. So here's your example. And I'm going to need your help. Let's think about a bank account that we're going to take the money in the bank account and we're going to invest it in the stock market. We're going to buy some Tesla. We're going to buy some Facebook. All right. We're going to hopefully see our stocks go up in value. We're going to buy some Bitcoin. Now, by the time later people watch this video, all three of those stocks may have tanked. But Bitcoin's a cryptocurrency right now. It's rocketed up. Facebook has rocketed up. Amazon has rocketed up. Tesla has rocketed up. These stocks, if you look at their If you look at their growth patterns, looks like this year. That is an exponential growth pattern in the stock. Okay, guys, so look, we want to know the future value of our stocks. Okay, so this is the thing we are seeking is Y, which is going to be our stock's value later. So put Y equals. And now I need to know from you, how much money did we put in the bank to start with? You can make up any number. What do you think we should start?
50,000.
50,000. So put 50,000. And this is $50,000. Okay. Now put an open parentheses there. Now here's the question. What percent return or what percent growth do you think we will see in those stocks? What I mean by that is every year that we have invested the stocks, we should expect to see something like 10, 20, 30% growth.
I was thinking about 40%.
40% growth? Okay. So if you want 40% growth, you put 1 plus 0.40. Now, this was the key. Keith said 40%, and I converted 40% into a decimal. Okay? That's how I got 0.4. If he had said 37%, this would be 0.37. If he said 5%, it would be 0.05. Do you understand how I'm coming up with the 0.4?
Yes.
It's very important because in all the problems, they're going to give you a percent, and you have to always convert to decimal. Okay, just close the parentheses now. And we want to know how many years do you want this money to be in the stock market? How many years?
Let's say 25.
What you put this input? I'm gonna go with him. 25 years, okay? Put a 25 up here.
He said 10.
Oh, sorry, that's what you said. Okay, so 10. Okay, so the way we're gonna figure this out is we're gonna go to our calculators. Okay, so what you want to do is you don't need to be in Y equals. I just want you to put this in your calculator. And I need to show you how to do that. Let me stay out of the way, but also open this calculator up. You're going to see a huge number.
Yeah.
It's going to be, I think, millions. I think it's going to be millions. Okay, let me jump over here and see if I can't.
You're looking at $1,446,200.
So we start with 50,000, and then that parentheses is multiplication, and I'm going to go ahead and just put 1.4, right? Because 1 plus 0.4 is 1.4. Okay, and then I'm going to hit this character right here. You see this guy? We call it the house top, and that's where I can put 10. Yeah. Yeah, $1.4 million after 10 years. So the amazing thing about exponential functions is it just took 10 years to go from 50,000 to 1.4 million. Okay, that's a lot of growth. So what I want to show you is the picture of what you created there. So for this, I'm going to go to Desmos. And I'm actually going to type this out like it's an equation. So watch how I'm typing this, folks. I'm going to type y equals 50,000, open parentheses, 1.4, close parentheses. Now I'm going to hold down Shift and 6, and that gives me the exponent position. And I'm going to type an X. If I type a 10, it's going to show me a flat line. It's going to show me a number, okay? But if I type an X, it's going to model the actual function. So let's see what that looks like. We're going to need to zoom way out because our starting value is 50,000.
That's not true.
Do you see how it's almost vertical?
Straight up.
I would need to fix the scale here because the scale isn't working. I'm going to start the x-axis at 0, and we'll put the end of the x-axis at, how long are we investing? 10 years? So I'll go ahead and put it at 20. And then the y-axis, I'm going to start it at 0 and put it at, it was 1.4 million, so I'll put it at 2 million. Now it's going to look better. Let me zoom out. Do you see that? Does that have that characteristic? It looks like a hockey stick, okay? Do you see it looks like a hockey stick? It starts off small. Look here, in year 1, after 1 year, you've only got 70,710. After 2 years, you've got 98,000. After 3 years, it's jumped up to 135. By 10 years, you see it's gone all the way up to over 1.4 million. So the growth in the beginning is relatively slow. The numbers aren't changing dramatically, but after a while, there's an effect called compounding, where the effect becomes magnified with each previous year's growth. And so the next year is even bigger, and the year after that is even bigger, and the year after that is even bigger. Yes.
If you wouldn't mind just doing the 25 real quick, just so you can see what the number is.
Oh yeah, so if I put in 25, here we can actually, you see if we go to 25, look how this graph looks. It starts to go straight vertical. If I put in 25, it's really easy to change this number. You just go up, up, and then enter, and then you can just hit the left arrow and go change this to 25. So that is 224, wait, yeah, $224 million. This is how people become billionaires, okay? They start small, and then they hang on to a high growth stock or stocks portfolio of stocks for 25, 30 years. And this is how you get people like Bill Gates and Warren Buffett, who have hundreds of billions of dollars. Jeff Bezos, hundreds of billions of dollars, okay? We should. Right now, stocks are very expensive. Okay, so do you understand how we came up with those numbers? So this answer Y was 1.4 million. Okay. The key thing to know is that the X in the math problem is in the exponent position, hence the name exponential. All right. I think that's a good place to stop with like the lecture, because that gives you the kind of a good foundation. I don't have much more to say about the topic right now, so we'll stop there with the lecture.